Hello everyone. We're going to talk about section 10.2, properties of liquids. The learning objectives here: distinguish between adhesive and cohesive forces, define viscosity, surface tension, and capillary rise, and describe the roles of intermolecular attractive forces in each of these properties or phenomena. So this is going to be a very descriptive section in terms of we're getting a brief overview of some of these properties, but we're not going to get into a lot of detail here. These are things that can definitely be measured, and there are calculations that can be some very, sometimes very elaborate calculations that can be done on some of these. We're just going to explore this from the perspective of, okay, these things exist, do you know what they are? So the first one your book talks about is the word viscosity. And this is a measure of resistance to flow. And the units and physics kind of involved in that is a little bit more elaborate. So we're not going to get to that level of detail. Just think about some flowing things and how some things flow easily and some things flow more difficult. So for example, if you put honey or syrup on some of your food, you know that it comes out pretty slowly. Whereas if you're pouring yourself a glass of water, it comes out pretty quickly. So we would say that something like water has a low viscosity, whereas something like honey or syrup would have a very high viscosity because they are resisting that flow more so than the water is. So that is viscosity, and we have some pictures of that here. And of course, I think this is something that comes up a lot in motor oil commercials. We're not going to get to that level of detail either, but just something you probably have heard of in that context. We have a table here with some units of viscosity. Don't worry about understanding what the units mean, other than lower numbers are lower viscosity, higher numbers are higher viscosity, and you can see some of these are very, very high, and some of them are quite low. So there's a lot of big difference between water and honey there, you can see. And the reason for this is there's a lot of things that can affect this, but essentially the intermolecular forces are a big deal here. So the larger those are, the greater the viscosity, and in some cases you have other things affecting those intermolecular forces beyond just what we have talked about so far. But again, we're not going to get to that level of detail. We can zoom in a bit more and talk about some of the forces that are going on. And one of those is called a cohesive force. This is the force that exists between molecules of the same substance. Again, all of these are for a liquid phase, okay? So viscosity, liquid phase, cohesive force, liquid phase. And it turns out there are differences in cohesive force based on where in the liquid we have the molecules. And you can see that when we look at some of these little water droplets. They tend to form spheres, and there's a reason for that. If you look at a water droplet in the center of the sphere, anywhere inside the sphere, it has these cohesive forces between all of the other water molecules around it. Whereas if you look at a water molecule on the surface of the droplet, it doesn't have as many of the cohesive forces. So it has fewer cohesive forces. And it turns out the way this works, again, this is these cohesive forces are essentially the intermolecular forces, right? And they're talking about the stickiness that those molecules have, their tendency to stick together. And the forces are such that you typically will want to have a smaller area for your droplet of the liquid. So the best way to do that is to form a sphere. So they form these spheres so that there are fewer molecules on the outside and more molecules on the inside. And it turns out the bigger the sphere, the more you minimize that. So if possible, when you put two water droplets together, they will merge into one to minimize that surface area. But when they're not next to each other, they're not going to do that. So those are cohesive forces. And we basically already talked about surface tension, and that is related to this difference between cohesive forces on the inside and on the outside. So because of this, there is an energy necessary to change the area, the surface area of the liquid. So to make it have a larger surface area, that's the surface tension. And because of this energy, we can sometimes get things to float on top of a liquid that are more dense than the liquid by just a little bit. So there are some ways of doing that. You may have seen ways to kind of try to float a paper clip on top of some water, for example. And that's because the surface tension of the water is such that it doesn't want to disrupt that surface area. And so the force of the weight of that paper clip, or there's some bugs that walk on water, for example, isn't enough to make it sink. So there's a balancing out there. And here's a picture of one of those bugs walking on the water. And again, you can see because of the difference between the inside water molecules and the water molecules on the surface, it is able to, even though it might have a greater density than the water right here, it's able to support itself because of that little bit of difference. Again, don't worry about the units or the numbers here, but you can see some different surface tensions we're showing here. You'll notice that the water is, so mercury is very high, but water is much higher than things like octane. So this would be like gasoline, or these other organic liquids. So water has tends to have a fairly high surface tension, and other things do not. So this bug would not be walking across an oil spill, for example. Okay, so we've already talked about cohesive forces. We also have what are called adhesive forces. These are between different molecules. So we can have intermolecular forces between things that are different, and we'll explore that in a bit more detail in Module 11 for things like solutions. But when you have a liquid in contact with a solid, you could have adhesive forces. So here we're looking at some differences between mercury and water. And this is something we've known all semester is true, because you've known that when you measure the volume of water, you measure the bottom of the meniscus. Okay, and so we know that this thing exists. We know that when water is in a glass tube, it will tend to bend up towards the surface of the tube. When mercury is inside of a glass tube, it doesn't do that. It bends downward. And so what's going on here is you have similarities between the water in the glass. So the water is attracted to the glass, and there's a tension there between the weight of the water and the attraction to the glass surface. And that is an adhesive force. And we can see if we get, so first of all, understand that this is true. We have a attraction between the water and the glass surface. And so the kind of the constraint there is the weight of the water is pulling it down in the middle. So you might imagine if we made that glass if we shrunk it, eventually we might have something where there's a really strong attraction between the glass and the water, such that it doesn't, the weight of the water doesn't overpower it. And that is actually what we do see, and we can identify this with something called capillary action. And this is because there is an attraction between the liquid and a solid, and that attraction leads to the liquid moving through the solid. So here we're showing some examples of that. So if you think of a liquid wicking up a solid, like here we're showing wine with a paper towel where the wine is kind of, wicking up it. And so, it kind of climbs the surface of the solid. That is a capillary action, is what's causing that to happen. And here we're showing capillary tubes. And we can see if we stick these very thin tubes into a sample of water, the water will climb up the tube because the attraction between the water and the glass is greater than the weight of the water. So we can overcome that and climb up that tube. So there are, it's possible to do the math to figure out those relationships. We're not going to do that here. But if you do the same thing with mercury, what you would see is that it actually goes down. We have this capillary repulsion, and here you're looking at, well, if it's going down that much, then that means the mercury on the outside is going up a little bit, so it has to counteract the rise in the mercury on the outside relative to the inside. So that is capillary action. So this is the equation. Don't worry about the equation. We're not going to use it at all. We want to have just an understanding of what these terms are is sufficient for this class. So that is section 10.2. Feel free to move on to the next section.